All right, great, thank you. It's a real pleasure to be here today with all of you. I'm really looking forward to the next day and a half. I'm a biomedical informatician. I'm director of the Institute for Biomedical Informatics at the University of Pennsylvania. And more specifically, I'm a methodologist. I've spent my career developing machine learning and artificial intelligence methods with application to clinical, genetic, genomic, environmental data. And what I want to do today is give you an introduction to AI and machine learning, tell you about some of the challenges, but also introduce a user-friendly software package that we've developed to automate machine learning. And my claim is that our software is so easy a 2-year-old can do it, which means all of you can do it. All right, so from an environmental health sciences perspective, this is how I think about environmental health. We have one or more toxic exposures, and what we'd like to be able to do is predict their impact on molecular interaction, cellular response, physiologic response, all the way to human health. And so from a machine learning and AI point of view, this is what we want to do, right? Given some exposure, we want to predict what's going to happen either at the biological or cellular level or at the organismal level. Now, for us to be able to predict these kinds of things, we have to understand how all the different components of the system work together. And health really is a complex system. It's many genes, many environmental factors, all working together in a complex way to determine each individual's trajectory through time toward a complex clinical endpoint, such as bladder cancer. This slide's for you, Margaret. So here we have arsenic, and what we do in epidemiology and biomedicine is we often take a single factor out of this complex picture and try to use it to predict a complex clinical endpoint, completely ignoring all of the biomolecular interactions. And so I think this is where machine learning comes into play, because machine learning is really ideally suited to looking at lots of factors simultaneously and, importantly, modeling their interactions, the complexities of the relationship between all of these factors and some clinical endpoint. All right, so for those of you not familiar with AI, let me give just a very, very brief overview and history. Artificial intelligence is the basic idea of whether we can get computers to plan, solve problems, and reason. And Alan Turing, the great computer scientist, asked in the 1950s, can machines think? And how would you know if a machine could think? So imagine getting out of bed this morning, you log into your favorite social media platform, you have a conversation with your friend. Later that day, you see your friend and say, boy, that was a great conversation we had. And your friend says, you weren't talking to me. I was still sleeping. You were talking to my computer. At that point in which you can't tell the difference between whether you're talking to a real person or a computer, the computer is said to pass the Turing test. Now, we've been talking about the Turing test since the 1950s, and we're now in that period of time where computers are starting to pass the Turing test. So we're in that exciting window of time that people have dreamed about since the 1950s, and I'll show you a quick example of that. Now, for AI researchers, there are two basic approaches. The top-down approach is to build a machine that mimics how the human brain works. So if you remember Data from Star Trek, right? Data had what Isaac Asimov, the great science fiction writer, called a positronic brain, right? An artificial brain that mimicked human behavior. Now, turns out that's really hard, right? We don't even understand how the human brain works. How are we going to develop an artificial brain? So there are people that work on this, but this is the really hard part of AI. What most of us do is bottom-up AI. We take simple mathematical components, we piece them together, and collectively they exhibit a complex behavior, like deep learning neural networks, right? Can take images and classify them very accurately. So that's what most of us do. Now, interestingly, the phrase AI was coined at Dartmouth College in 1956. At a workshop, a lot of the AI leaders in the field at that time came together for, I think it was a couple-week workshop. So they came together and spent the summer together. And what they realized was that they were all calling artificial intelligence something different. And they wanted to unify the field behind one name that they could get behind. And that's how the phrase artificial intelligence came about and became standardized in this field. Now, AI has had a very interesting history in medicine, going back to the 1950s and 60s. So if you think back to World War II, that's when computers first came on the scene. And during the 1960s, computer technology started to advance. And everybody who had been dreaming about AI, more from a science fiction perspective, could now start to think, wow, we can realize this because we can actually program computers to do artificial intelligence. So there was a lot of excitement and a lot of hype through the 1970s as personal computers came on the scene. So if you remember 1977, that was a big year. That was when the Apple II computer came out. That was when the Commodore PET and the Radio Shack TRS-80 computer came out. It was also the year of Sanger sequencing, and the year of the internet was first demonstrated. So that 1977 was a big year. So there was a lot of excitement, a lot of hype. And then as we started to implement AI algorithms on early computers, there was a realization that, okay, these things are not working as well as we had promised. And that led to what we've called the AI winter, where AI became a bit of a dirty word. And if you were an AI researcher, you didn't want to admit you were an AI researcher, at least not in public, because people would think you were crazy. Why are you working on those things that don't work? That's just science fiction. So we went through this period of time, this kind of dark period of AI. But then something happened in 2010 that changed all of that, and that was IBM Watson. And you'll remember IBM Watson came on the scene and beat the Jeopardy champion. And that was, I think, the first real demonstration of AI being human competitive, right? And the Ken Jennings, the Jeopardy champion at the time, was a very impressive individual. And so this was an amazing feat. It combined a lot of computer science technology, natural language processing, information retrieval, machine learning. The computer that beat Ken Jennings had 200 million pages of information, 4 terabytes of data. Most of that was a dump from Wikipedia. So they just took everything in Wikipedia and some other encyclopedias, dictionaries, et cetera, and put that in a database. And then they had 2,800 compute cores. So they had a supercomputer, and this was IBM's specialty. 16 terabytes of RAM, and of course no internet connection, because human players didn't have access to the internet. Now, if you think about this, this is really impressive. So if you think about playing Jeopardy, you have to read the answer. You have to think about what you know about that answer. So you have to access your memory. Then you have to formulate a question. Then you have to decide what's the probability with which this question's correct. You have to make a decision, am I going to buzz in? And then you have to physically buzz in. All that has to happen in less than 3 seconds. So the fact that a computer could do that is really remarkable. And that's why many look at this as a real turning point. I remember being at a National Library of Medicine meeting, and the director made a big deal about this. He was so impressed, Don Lindbergh was so impressed with IBM Watson, and remarked about what a turning point, what a milestone this was. Now, IBM, of course, riding on the success of Jeopardy, decided that they were going to build their whole business model on this. And so they rolled out IBM Watson for oncology, and they started marketing this to cancer centers. Memorial Sloan Kettering and MD Anderson and some others signed on and paid many millions of dollars to IBM Watson. And these cancer centers started putting it to the test. And what they discovered was that Watson really wasn't quite ready for prime time and could not prescribe chemotherapy for cancer patients better than an oncologist could. So that was a bit of a setback for IBM. And in fact, MD Anderson pulled out of Watson after spending $60 million on it. That's a lot of money, even for MD Anderson. So that generated a whole bunch of negative headlines. This is my favorite negative headline. IBM Watson is the Donald Trump of the AI industry. I think that's a little, I don't think IBM deserved that. I think that was a little harsh, but, and you know, IBM, it's not that Watson's not a great technology. It is a great technology. The mistake that IBM made is they pushed it out into the marketplace too fast. It really needed about another 5 or 10 years to cook. They tried to corner the market. This was purely a business decision on IBM's part. They tried to corner the market on artificial intelligence. They tried to squeeze out all the competition. And in doing so, they really shot themselves in the foot again. And there were people embedded in these negative headlines worried that we might enter a second AI winter with the failure of Watson. So I don't think that's happening. But anyway, it's an interesting story. And if you're interested in the story of Watson, this just came out about 2 months ago in IEEE Spectrum magazine. It's a nice overview of the Watson story and its successes and failures. Now, I mentioned that there are examples of computers passing the Turing test. This is one. This is Google Assistant. And if you haven't seen Google Assistant, when you have a break, go and look on YouTube and find the video of Google Assistant making a haircut appointment. So this is a computer that can dial dial up to make a haircut appointment, talk to a receptionist, schedule the appointment, hang up the phone. The receptionist has no idea they're talking to a computer. It's very lifelike, even with human-like pauses and ums and the kinds of things that we say in our informal speech. Now, interestingly, there's also a video on there that you can find where Google Assistant calls a non-native English speaker to make a haircut appointment, and that completely goes off the rails, so it's not perfect. All right, so I'm interested in AI. Now, the way I think about AI is, and I differentiate it from machine learning, that AI is really about getting a computer to do something that we do, right, that we as humans do. Whereas machine learning is really a subset of AI looking for patterns in data. Now, I'll give an example of that in a minute. Now, I'm interested in, can we get computers to do data analysis for us? Machine learning is really hard. And as I'll show you in a minute, there are lots of different machine learning methods, lots of different parameter settings. And so I'm interested in, can we automate this process so that absolutely everybody can do machine learning? The technology's there, as I'll show you in a minute. So why artificial intelligence? So again, back to this idea of humans. If I was to give everybody in this room a data set and say, let's come back next week, you can do any analysis you want to, you can do as many analyses as you want to. We'll come back next week and compare notes. Each of us would take a different path through that data set, right? Based on our training, our experience, our knowledge. Some of you might be statisticians, some of you might be informaticians, some of you might be biologists. But everybody would take a different path through that data set. And we as humans are natural tinkerers, right? Whenever we get a new data set, when you get a new set of data from your experiments, you start trying different things. What's there? You look at the data, you try different analyses, you see what works, what doesn't work. And what ultimately ends up in publication form is often the best result, or the result we trust the most. But we often try a whole bunch of other things that sit on our hard drives and go away and never see. So I'm interested in this process. How do we as humans analyze data? How do we make decisions? How do we learn from that? And can we get a computer to do that? So that's the AI piece of this. All right, so here's how I think about the data analytics pipeline. So here we have a bunch of data, diverse data. The first thing we want to do is integrate that data, bring disparate data sources together so we can answer an impactful question. Now, these next three pieces here are really the guts of the machine learning part of this. So the first thing you might want to do, assuming you've got big data, and we often have big data now with thousands or even millions of features, variables or features. So the first thing you might want to do is do what's called feature selection. Identify a subset of the variables that are the most informative so that the problem is more computationally tractable. So for example, if you're doing a genetic study, you might pick a particular pathway of interest. If you're studying diabetes, you might look at insulin metabolism, right? And that would be a way you could use your biological knowledge to focus in on a particular pathway. Or if you're doing an environmental study, a toxicology study, you might look at DNA repair pathways. So feature selection is important to try to hone in on those things that are the most informative. The next thing you might want to do is what's called feature construction or feature engineering. That is, the variables might not come to us in the right representation. We might not need to recode them. We might need to combine them in ways that make sense. Okay, and then the next step is then to do the machine learning. As I said, there are lots of different machine learning methods. Each one looks at the data in a different way. And picking a machine learning method can be very challenging. Now, assuming you've done all of this correctly, the next step is to interpret it. And I would argue that interpretation is probably more challenging than all of the computational work that goes into this. And I'm sure we'll talk a lot about that in the next day and a half. And then you want to validate it, maybe take it into the laboratory and convince yourself it's real. And then ultimately, we want to move it into the clinic and help people. So I'm interested in this middle part here. Can we automate this? And I'm going to focus on this machine learning piece here. Now, for those of you not familiar with machine learning, this is a nice illustration. If you Google machine learning and visualization, you'll find a couple variations of this figure. And this is a really nice illustration of what machine learning is doing. So here we have three different data sets. And maybe we have a case control study. We have red cases, blue controls. And the X and Y axes are two variables, okay? Maybe age and body mass index, and maybe we're trying to predict cardiovascular disease from healthy controls. And what machine learning is doing is it's trying to find a mathematical function that separates the red dots from the blue dots as optimally as possible. And here listed are 3 different machine learning methods. And what you can see is that each machine learning method is looking at the data in a different way. The linear support vector machine is drawing lines through the data as a linear separation of the dots. And then the support vector, the radial basis support vector machine over here, you can see is drawing circles or curved regions around the data. Now, what you can also see, the numbers here represent the proportion of subjects that are correctly classified by each method. So the bigger the number, the better. So down here in this bottom data set, you can see the linear method does the best at 95%. But on this second data set here, the linear support vector machine is the worst method, and the other 2 methods do much better. This circular pattern is much better than the linear pattern. So the point I want to make with this slide is both to communicate, in some sense, what machine learning is doing, and then in another sense, every machine learning method looks at the data differently. It's looking for different patterns. And this is one of the challenges of machine learning is you don't know when you start which machine learning method you should pick for your data set because you don't know what the patterns are that you're looking for. So this is motivation for automating this process, and that's what I've spent a good part of the last 5 years focusing on. So what I want to introduce to you is Pen AI. This is an open source, user-friendly, completely transparent artificial intelligence system for automating machine learning, okay? So I'm just going to step you through the pieces and parts of this. So we started working on this project about 2 years ago. So the first thing we needed, so what we want is a computer that can do machine learning automatically, learn from that experience just as we as humans do, get better, and then do better machine learning in the future on new data sets. All right, so the first thing we needed was a machine learning toolkit. Fortunately, we didn't have to develop that ourselves. There's a very nice, comprehensive machine learning library in the Python programming language called scikit-learn. It's completely free, it's open source. It's very professionally developed. It's probably the most widely used machine learning library in the machine learning space right now. And it does everything that you want it to do. It does discrete classification, it does regression, it does unsupervised cluster analysis, it has a bunch of pre-processing algorithms, it does things like principal components analysis. So it's very, very comprehensive. The only thing it doesn't do yet is deep learning, but it does just about everything else you would want it to do. So the good news is we didn't have to build this, so we were able to take advantage of an open source tool as our machine learning library. The next thing we needed was a controller. Remember, the computer's going to do the analysis, so we need a way for the computer to grab your data, grab a machine learning algorithm, run it on a server, and get a result back and do something with it. Now, we started coding this ourselves, and then I discovered an open source project that had just come out on GitHub called Future Gadget Lab that did exactly what we wanted to do, exactly what I described. So that saved us a couple months of development time, so we incorporated this. That was very nice. And then the next thing we need is a database, right? We need a memory. If a computer's going to learn over time, then it needs to have a memory. And as I said earlier, when we do analyses, most of those analyses disappear, right? They sit on a hard drive and they eventually get deleted. Or maybe you archive it, but you never look at it again. And so what we want is a database. So every machine learning analysis that's done with this system goes into a database so we have a complete memory that we can learn from. Now, we used another open source, freely available tool called MongoDB. MongoDB is a database called a document store. So think of every machine learning result as a piece of paper, okay? You've got on there the data that you analyzed, you've got the machine learning method and parameter settings that you used, and then you've got the results embedded in there. Okay, so they're all coded on a piece of paper. The piece of paper goes in this document store, gets filed away, and then you can retrieve those documents through keyword searches. Now, this kind of database is very appealing because it's very easy to get results in and get results out. Relational databases, as many of you know, are very expensive and time-consuming to develop. Okay, so now we have our machine learning code. We have a way for the computer to do that automatically. We have a database, which is the memory of the system. The next thing we needed was an AI algorithm. Now, this is where our primary research is focused over the last 2 years is How is the computer going to learn? What is it going to do? How is it going to look at all that information and get better over time? So the way we do that is from that database, we extract all the machine learning results and put it in a table like this, where every row is a different machine learning analysis. The last column here is the performance. The bigger the number, the better. This is the area under the ROC curve for balancing false positives and true positives. And so the bigger this number, the better. So every row is a different machine learning analysis. We have an indicator variable for the data set that was analyzed. We have an indicator variable for the particular machine learning method and parameter settings that were used. And then we have these things called meta features. Okay, these are characteristics of the data. So you could imagine that machine learning methods are going to depend on the size of the data, the distribution of the data, the type of variables that are there, the correlation structure of the data. So we have over 100 different of these meta features that we capture and put into this table. So this is the context with which a machine learning method might work. So we have this data set, and then what we do is an analysis on this, and I'll show you in a minute some comparison of different analytic methods that we use to create the knowledge that the AI algorithm uses. So the AI, you can think of this as kind of like what we call a recommender system. It's like when you go on Amazon, and Amazon recommends to you something that you might want to buy based on your shopping experience and everything else it knows about you. That's what this is doing. It's recommending a machine learning algorithm based on its experience. All right, so the next thing we needed was a way for 2-year-olds to interact with this. So this is what we came up with. This is the interface. When you log in, you see your different data sets here. It shows you, for this diabetes data set, there are 26 results in the database, 26 different machine learning results. It shows you the best one, so it gives you a little snapshot of the best result and the accuracy of its best prediction. And then we have a button here. This is the AI button. So all you have to do is load your data as a CSV file, like a tab-delimited text file in CSV format, and then push that button, and you're doing machine learning. The computer takes over and starts launching what it thinks are the best machine learning jobs on your data automatically. And you can set a limit for how many you want them to do or how long you want it to run. So it's that easy to do machine learning. Now you can do an interactive machine learning analysis by pushing this blue button here. And so we've have some preset machine learning methods here. You select the machine learning method, you push buttons for which parameter settings you want, you hit go, runs on the server, the result comes back and goes in the database. So we make it super easy to do an interactive machine learning analysis. Anybody can do this. Then we have a tab. This is all web-based, by the way. We have a tab here where you can go and explore the results. So here's all the results for that diabetes data set. You can sort them by accuracy from best to worst. We have an action button over here. You push that button, two options. You can download the model, and you can download the Python code that generated the result for that model. So full transparency, the Pen AI writes the code for you. You can take that code, you can go validate it, you can incorporate it into other software, you can do whatever you want with it. Now we're going to add a feature here. We haven't added this yet. We just released this a few weeks ago, but in the next release, we're going to add a feature here where you can load a validation data set and then apply that model to the validation set within Pen AI if you want to validate a model. All right, now if you click on one of these results, we have a nice dashboard that shows the training and testing accuracy. This is from tenfold cross-validation. This shows the ROC curve. And then we have these things called feature importance scores, which are, this is part of the interpretation. So what we do is we take each variable in the data set, we randomize it, we repeat the analysis and see what the impact of that feature is on the overall result. So the change in the performance is a measure of how important that variable is. And then you can see here what rank order, what the most important variables are. Okay, so Pen AI is open source. Like I said, we released it on GitHub a couple weeks ago. It's super easy to use. Unfortunately, it's not that easy to install. For those of you that are more informaticians or computer scientists in the room, it's built on a couple different Docker containers. So you have to have Docker installed, and so you probably need some IT help to get this installed. But once you have it installed, it's super easy to use. And then we have an evaluation paper that's on archive that we just put out about 2 weeks ago, and we're getting ready to submit that for publication. And that's what we did in that paper is we put PenAI through its paces. We said, okay, let's take 150 real data sets, let's present them one at a time to PenAI and watch how it learns. And then repeat that process with a different ordering of the data sets and do that many, many, many times so we can watch how it learns. And we know what the best machine learning algorithms are in these data sets. We've done a comprehensive and exhaustive analysis of all machine learning methods on the data. And so this is what the results look like. These are our different AI algorithms that are looking at creating knowledge for the recommender system. And this is the number of data sets as it's experiencing more and more data sets as it goes. And it gets better and better. And a singular value decomposition method so far is working the best, and that's what we have in PenAI. So when PenAI experiences about 200 or 300 data sets, it's getting pretty close to nailing the right machine learning method most of the time. We have a webpage, penai.org, where you can get more information about it. And I'll just stop there and thank a couple people. Heather Williams is the lead software engineer that built the release version of PenAI. She was assisted by Wei-Shan Fu, a programmer who did a lot of the coding. Sharon Tartarone developed the web interface for that, and she did such a beautiful job that the New York Times hired her. She works for the New York Times now. This is largely funded by funds from the University of Pennsylvania, but I'll mention Bill LaCava is a postdoc in my lab who built the recommender system. These are my R01s that fund this research, my email, and I'm on Twitter at morejh. So I'll stop there, and hopefully there's time for a question or two.
So if there are questions, please go to the microphone so the people online can hear.
I guess I have two questions. The first is that if you just have a bunch of data sets, it doesn't know what you're interested in, and it doesn't know the structure of the data set. So how does it know what the outcome variable is, and how does it know if there's some other complications of the data set? I guess you're just focusing on cases where you have like a simple classification, so there's some class label, and then there's a bunch of features, but everything else is not in any intricate structure.
Yeah.
And the second question is, I guess if you have a bag of machine learning algorithms, then it's sort of well known that the best thing isn't to take one of the machine learning algorithms, but is to take an ensemble of the machine learning algorithms. And so you think that potentially one direction here would be to, as you learn over a bunch of data sets, you learn better aggregation weights across the machine learning algorithms. And that would presumably do better than zooming in on any one of them.
Yeah, those are both good questions. So first of all, we have a specific data format, so the PenAI knows what your outcome variable is. And right now we're just doing discrete classification. We do plan over the next year to add in all the regression stuff so that you can do regression problems with it. And I would say, what you should do when you put your data together is really focus on a particular question that you're interested in, so that PenAI, is so that the output of PenAI is more directly geared toward answering that question, rather than feeding it a giant data set and letting it swim around in that data. So I'm a big fan of doing the feature selection that I talked about in a way that focuses your data around a specific question. For the ensemble learning, I completely agree. And I think it's important to step back and say that we developed this not for computer scientists, not for informaticians, not for statisticians. We developed this for everybody else so that anybody can do machine learning. And in that goal, we really wanted to streamline and simplify this so it was accessible and understandable. We didn't want to layer in a bunch of computer science stuff that people wouldn't understand or couldn't get beyond. Now, with that said, over the next year, what we plan to do is layer in the background some of these more complex methods like ensemble learning for people who understand what that is and can interpret those kinds of results.
Do you conform to a standard for storing all of your runs in the Mongo database, or have you published your schema as a standard?
It's all in JSON format.
Okay, but there's no specification that it's checked against or anything like that?
Well, the future Gadget Lab controller software that I mentioned, that's what it uses. It encodes in JSON format. So you can go to that project and see exactly what their specification is. And that's what we use. And we just dump those into MongoDB.
Okay, thanks.
All right, thank you.